All right. I will begin. Dear Father, we thank you for this morning. Thank you again for this class and this opportunity we have to study your creation. Just pray that you give us insight today, help us to glorify you what we do, and just to understand this material, Lord. In my prayer, Lord Jesus. Amen. So today, talking to you guys about the singular value decomposition, which I have to say from the outset, calling these values singular values, as I think about what the word singular tends to mean in the larger context of things, it's a really weird label. It's a really weird label, because it seems to me like they're the opposite of singular. But whatever. I'm just saying, I object to the name. But here it is. So it is nonetheless an important decomposition, and after we work it out, it does actually have some pretty interesting geometric insight, which I'll try to take a minute or two to talk about it when we get there. So the singular value decomposition. So this is first for a rectangular matrix. All right. So you have a m by n matrix, right? And so if that's the case, it's going to take us a little bit to derive. There's like probably a page of theory here, but we need to go through it, otherwise it would just be complete and total, it would just be really, really weird to just teach you this as an algorithm. It would be very, very strange. So let's not do that. So we start with the matrix, and then one of the key ideas is to notice that A transpose A, right? And I'm going to, for the sake of convenience, I'm going to call that thing B in here, is a n by n matrix. And what can you tell me about B transpose? Nope. So sock shoes, right? So what's the transpose of B is equal to? B again, all right? So B is a symmetric matrix, right? It's an n by n symmetric matrix, in fact. So therefore, hence, by the real spectral theorem, there exist eigenvalues lambda 1 greater than or equal to lambda 2 greater than or equal to dot 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 greater than or equal to lambda. Well, I'm going to introduce some notation here. I'm going to say R is positive. Oh, rats. Let me just say n for the moment. I'll come back to this. I have to. All right. To start with, that's all we have. We just know that there are real eigenvalues, and we can put them in order, and you know, v1, v2, vn is orthonormal. Right. That was our theorem of Rn. All right. But there's a lot more you can say here than just that. So let's calculate if we look at the length of A times VI, what's that going to be equal to? Let's square it. Squaring length is nice, right? So the squared length is AVI dot AVI, right? But if we write that as a matrix product, remember the dot product is the transpose, so we've got like AVI transpose times AVI, which is VI transpose A transpose A times V. Yeah. And then what? Now, I guess I should emphasize here, it's an orthonormal eigenbasis. And it's an eigenbasis for B, which is A transpose A, right? So what we have is that A transpose A times VI is equal to lambda I VI, right? That's the assumption of the spectral theorem here, right? That that the symmetric matrix is orthonormally diagonalizable, and as such, we can simplify this, right? What is that? See this right here? That's exactly lambda I VI, right? So I've got, and then lambda I is a constant, so I can pull it out. So I've got lambda I VI transpose VI, right? But what is VI transpose VI? VI dot VI, and we assumed VI is a length 1 vector, right? See this normal right here? So this is actually just equal to lambda I. Excuse me. Thus, the magnitude of AVI, the length of that vector squared, is equal to lambda I, right? So this tells us something about the eigenvalues. What does it say? Could they be negative? They cannot, right? So these eigenvalues for B, for the A transpose A matrix, they are non-negative. They are greater than or equal to 0. All right? And so for that reason, so then we can just define lambda R to be smallest positive, eigenvalue here. So what does that mean? That means that we have lambda 1 greater than or equal to lambda 2 greater than or equal to greater than or equal to lambda R, right? And then past that, that's greater than 0, right? And so like 0 is equal to lambda R plus 1 all the way out to n. All right? Because we're just labeling them stupidly 1 through n. So it may be that lambda 1 equals to lambda 2 equals, they may all be equal all the way out to R, right? But past R, they have to be 0 by construction here. All right? In fact, we can argue, here's a proposition. If we look at the set A, V, I equals 1 to R is an orthogonal set of non-zero vectors. All right? The proof is very, very similar to the calculation we've already done. So to prove that's orthogonal, I have to do what? I have to look at like A, V, I dot product with A, V, J. But what's that work out to? That works out to, my bad, VI transpose A transpose A Vj, right? But remember, Vj is an eigenvector with eigenvalue lambda j. So this is just lambda j, pull that out. Well, fine, one more step here. Vi transpose lambda j Vj, which I can pull the constant out. I've got lambda j Vi transpose Vj, right? Which is lambda j Kronecker delta ij, because we assumed that the basis, the v1 through vn, are themselves orthogonal. In fact, they're orthogonal and normal. Now, this is not an orthonormal set. Why? Now here, I'm assuming that I and j are greater than or equal to r. Okay? I and j greater than or equal to r. Therefore, this is 0 if I is not equal to j, and it's equal to lambda j if I is equal to j, which proves that this is an orthogonal set of non-zero vectors. All right? Do you guys agree? Disagree? What do you think? I mean, at this point, if you're like me, you're probably like, and? So, what's next? Well, here's what's next. If y is an element of the column space of A, right, then y is equal to a sum, not A. Oh, did I want A? Oh, it's fine. Y is an element of the column space of A. Then you guys tell me why I can write this. Why is it the case that y is equal to ci vi? Can you guys tell me why that is? What does it mean for that to be a basis for Rn? What are the two important things about basis? Remember, linear independent, and also everything in the space can be spanned. Where is the column space of A? It's a subset of what? It's a subset of Rn. See, because A is Rm by n, that makes, whoa, no, Rm, not Rn. Dudes, just a second here. Huh. Well, sorry guys, I have to think about this some more. It's not quite that. That's not the case. What does it mean to be in the column space? Of A. What's that mean? Yeah. Huh. All right, well, let me, I worked this out. I just tricked myself. There's one step I tricked myself, and now my proof's got a hole in it. I'm not sure I can fix it. So y is, what, like the sum, let's say k equals 1 to n of, let's say, bk column k of A. I think that's true. So there's n columns in A, right? And but the thing is, each column in A is actually a what? Oh, all right, fine. So, I mean, this is true because, I mean, that's essentially the definition of column space. Column space is span of the columns, right? And furthermore, notice that let's see here, AVI is equal to what? If I is equal to r plus 1, this is equal to 0 for I equals to r plus 1, and so forth and so on, all right? What's that say? On the other hand, whereas AV1 dot 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 AVR is, it's an orthogonal, right? So this is actually a linearly independent set. Remember we had that linear, if a set is orthogonal and non-zero, that implies linear independence. Oh well, sorry guys, there's a slight gap here, but long story short of this is that so that this implies that the rank of A, this implies that the rank of A is R. So like this implies that the dimension, and I haven't quite proved this guys, but the dimension of the column space of A is equal to R. Thus, you know, AV1, AV2, dot 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 AVR is basis for the column space of A. All right. So then what? So let me just recap. We have number one, we have that the column space of A is equal to the span of AVI, I equals 1 to R. And number two, if you look at this, we also have that, and perhaps I haven't quite proved this, but these assertions are true. VR plus 1 all the way out to Vn is basis for the null space of A. That's kind of readily apparent from these equations right here, right? Now the fact that it's a basis is just counting. Like the rank nullity theorem tells me that the dimension of the null space is equal to the number of columns minus the dimension of the rank. So if the rank here is R, then, excuse me, n minus R would be the nullity. So being that this is a linearly independent set of vectors which annihilates A, it says that that's a basis for the null space. And another way to look at the null space is it is actually what? It is actually the column space of the transpose of A perp. There's a new idea. Does that make sense to you guys? So what did we say about, like, would you remember what our formula was? Let me change the letters on us for a second here. What's the column space of M perp? What was the theorem we worked out? Remember, to figure out the perpendicular to a space, we take like the set of vectors which generate the space, right? Which in this case would just be the columns of M, and we transpose those, and we find the null space. So like this would be the null space of the matrix. You know, well I don't need it. It's already a matrix. So M transpose. So what happens here if you do the column space of A transpose perp? What's that? That's the null space of A transpose transpose, right? What's the transpose of the transpose? It's just A again, right? Okay, so taking my sweet time getting to the point here. So now we can make a construction. Let's take this set of orthogonal non-zero vectors and let's normalize them. So ui is equal to a vi divided by the length of a vi. All right? And that specifically is a vi divided by sigma I. Where sigma I is equal, in fact, to the square root of lambda I for I equals to 1 to ... to r. These sigmas are the so-called singular values. They're the singular values of A. So the singular values of A are like the square root of the eigenvalues of A transpose A. It's really kind of bizarre. But if you do this construction, what does this make? Then you've got u1, u2, ... ur, right, is orthonormal subset of what? Are they in Rm? Are they in Rn? Where are these guys? They're n vectors that have been rescaled, right? So this is a subset of R. Make sure I don't have my counting off. Every so often I make a mistake in here, you guys let me go. You know? Let's see here. So, see, in my notes I have as a subset of Rm. Is that true? Is it a subset of Rm or Rn? What do you guys think? Oh, I was just talking to myself. Look, here's what my error was. I'm thinking, but V is in Rn, right? Is AV in Rn or in Rm? Where is it? Where is this vector? You have m by n, right? Times n by 1. It's actually a what? It's an m by 1, right? So this is a subset of Rm. And what are the relations here? They have the defining relations a vi is equal to sigma I ui, right? Okay. What can we do if we have a subset of Rm? So two things could happen, right? Either R is equal to M. If R is equal to M, it's already an orthonormal basis for Rm, right? So if R is equal to M, then this u1, u2, ... ur is basis for Rm. And if we look at u equal to u1, u2, um, this is, has what? U transpose u equal to Im, right? What's the other possibility here? If R is less than M, then what? What can we do? And this decomposition is not unique. And the reason it's not unique, I think, pretty much rests on what I'm about to say. All right, because if R is less than M, what we can do is we can extend this basis U1 through UR to a basis for RM. And that process of extending a basis is by no means unique. So these are added. All right. Okay. Now, but then again, in this context, and back to here again, right? U equal to that is orthogonal. Excuse me. Now, if you look at this, we've got, let me recap here. We've got AVI equal to sigma I UI for I equals to 1 to R. And if we make V equal to V1, V2, Vn, this has what? It has V transpose V equal to the n by n identity, right? Also, the U, which we just constructed, is also orthogonal matrix. So like U transpose U is equal to the m by m identity, either whether or not we had to extend it. So let's put this all together. What do we have? If you look at the boxed equation, right? If you look at the boxed equation, we have that like AV1. If I do AV1, AVR, and then AVR plus 1, AVN, that is equal to a couple different things. On the one hand, it's equal to A times V1, V2, Vn, right? Because we have that property matrix multiplication. But on the other side, it's equal to what? Like sigma 1, U1, sigma 2, U2, sigma R, UR, and then zeros. So this could also be written as, well, you know, like sigma 1, sigma 2, sigma R, and then zeros times this matrix U1, U2, UR, and then UR plus 1, UM. So if I didn't do that wrong, I probably did it wrong. Yeah, I did that wrong. It's the other way around. Don't believe me. Grief. Come on, people. Not you, me. So how can I can factor out, I can rewrite this as, let me just write it out. This is U1, U2, UR, times sigma 1, sigma 2, sigma R, and then zeros. That's easy to check, right? So like I take the first column, I multiply this, I just get the sigma 1 U1 for the first column, then I get sigma 2 U2 for the second column, so forth. All right. Now this right here is what is called in the nomenclature like sigma, all right? And just to rewrite what we have A times V is equal to U times sigma, right? That's what we have, where this sigma has the singular values on the diagonal followed by zeros afterward. And then finally, solve for A. A is equal to U sigma V transpose. That is a so-called singular value decomposition. Of A. All right, let's try to work out. Let's try to work one out. So to recap, let me just recap the algorithm here before I step into an example. So the algorithm is basically this. To find the SVD, we simply do the following. Number one, find spectrum and orthonormal eigenbasis for A transpose A. And number two, define U sub I equals to AVI divided by the square root of lambda I for I equals to 1 to da 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 R. And this is the ugly part. Extend to UR plus 1 orthonormal if needed. I guess the step 3 is write down the boxed formula over there. That's it. This is not unique, and the reason it's not unique, in part, at least the part I understand of the non-uniqueness, is that the orthonormal extension need not be unique. So to recap, if you think back through it, any questions before I erase all the stuff that has answers to your questions? No? Okay. If you think back through this course, we have now seen how many different decompositions of a matrix? We started with what? the LU decomposition back in the day, remember that one? We had that one. Then what else? The QR decomposition. Of course, we have the whole diagonalization discussion. That's kind of a similar vein. We have the Jordan form of a matrix. That's general. The real Jordan form, I rather should say, is general. But yeah, I think this is pretty much it. I mean, there are other factorization schemes, guys, but not for this course. And I don't think even for 321. I'm not entirely sure we'll talk about all these in 321, honestly. Focus the 321 is elsewhere. So let's see here. There's a couple really nice examples in section 7.4, which is where I got this story and slightly mangled it. But let's see here. Where'd you gone to? Example 1. And these are nice examples. They're like, they kind of illustrate some of the difficulties, but they're not too hideous either. 4, 8, 11, 7, 14, minus 2. All right. All right, so first order of business, we need to calculate A transpose A, right, which I'm going to call D, What is that? Oops. I don't know how to transpose, apparently. Well, fine. All right, so we've got 4, 11, 14, 8, 7 to minus 2. That's my transpose. 4, 11, 14, 8, 7 minus 2. What's that give me? $16 plus 32? No. 16 plus 64, which is 80. Then we got what? 44 plus 56. That seems like 100, right? Then what? 4 times 14, 56. 56 minus 16 is 40. And I got 44 plus 64. Wait a minute, no, I'm done. Yeah, 44 plus 56. Oh, we should know this is 100 and this is 40, right? It's symmetric. You can check me on that. And then we've got 11 times 11 is 121. 121 plus 49, 170? Okay. 2 more to go. Let's see here. 14 times 14 is what, 196? Is that right? 196 plus 4, oh, that's 200. Nice.
Isn't that in the bottom right?
Oh, did I do the wrong? Yeah, thank you. You gotta watch me. I'll do dumb stuff here if I'm not careful. And then what? $14 times 11, 151 minus 14? Is that right? What's that? 14 times 11 is what? 154 minus 14 is, oh, 140? That sounds better. Thank you. Okay, great. Yep. Now, so something to know that's an interesting little trick about a matrix is that you can scale eigenvectors. So if I want to find the eigenvectors of this, I could just as well factor a 10 out and look at 8, 10, 4, 10, 17, 14, 4, 14, 20. You could find the eigenvalues of this, and whatever the eigenvalues are of that, 10 times that will be the eigenvalues of B. See, because there's a simple calculation you can do. See this, if B times V is equal to lambda V, then if I divide by, if I divide by C, 1 over C times B times V, right, is equal to lambda over C times V. So effectively, if you know the eigenvalues for one matrix, you know the eigenvalues for any scalar multiple of that matrix. It's something I don't emphasize enough. but it's terribly useful in making examples. Anyway, I don't really want to do either of those because we of course do not have time to calculate a 3x3 characteristic equation in here, right? So I will steal the results from the book, which are that this, when you work out, this has basically your V is 1/3, 2/3, 2/3, minus 2/3, minus 1/3, 2/3, 2/3, minus 2/3, 1/3. All right, so this is my V1, this is my V2, this is my V3, and you can pretty easily calculate that AV1 is equal to, I gotta work backwards from his singular values. Oh, 360. Wow. 360 V1. AV2 is 90 V2, all right? And AV3 is equal to, well, 0. Okay? So in this case, we have like lambda 1 is 360, lambda 2 is 90, and lambda 3 is equal to 0. So my R is equal to what? What's R equal to here? So what's that? 2. Yeah, 2. So I did your homework, guys. And the problems I've assigned, I don't think I actually, when I think they were such that A transpose A was like 2 by 2. So the homework problems are easier than this, if I remember right. But of course, you know, at this point in the course, if you did come against this in homework, you're free to use the, you know, the website to find the orthonormal eigenbasis. And once you find that, it should be clear how to go from there. You know, so like, what is? See, AV1 is what equal? What is AV1 explicitly? Guys, help me out. AV1 equals to? Can you multiply this times? Well, let's use this one, yeah. So AV1 is 10 times what? 8 plus 20 plus 8 over 3. See what I'm doing? I'm just multiplying this times this. I've got 10 plus 34 14 times 2, 28, yeah. You guys help me out if I get wrong here. Or 3, and then the last 2/3. Oh, why did I do 20 there? It should have just been what? Oh, I know why, because there's a 2 here. I'm a dummy. So, and then 4 plus I keep losing track of what I'm doing. 4 plus 28. 2 times 20 is plus 40. And I brought the 10 out. What's that work out to? 6, what's 36 over 3, also known as 12, right? So I got a 120. And what's this work out to? 72 over 3? What's that? 24 times 10, 240. And then what? 44 plus 28 So I think that's another 240, yeah. So that's AV1, right? Allegedly, if I haven't made a dumb mistake. And it looks like I made a dumb mistake. Oh, wait, what? Oh. Oh, A. I'm multiplying the wrong matrix, guys. Don't let me do that. Guys, come on. You guys gotta stop me. What am I multiplying right here? B. I'm supposed to be multiplying A, not B. A is up here. It's easier. Yeah? Duh. Some of you have thought about this like 3 minutes ago, but you doubt yourself, so you didn't say anything. Don't doubt yourself. Say something. Come on. So AV1. Factoring the 3 out. So I've got 4 plus 22 plus 28, and then I've got 8 plus 14 minus 4. So AV1 is actually simply a 2-component vector. That's nicer. And 22 plus 28 is 54 divided by 3. And this gives me what? 18 divided by 3? Okay, so we've got actually what? What's that? 18.6. All right, great. And that is equal to the square root of 360, right? Times 18 over the square root of 360, and then 6 over the square root of 360. (18 squared plus 36 squared is what? I hope it's 360. Because I'm pretty sure the length of this vector is the square root of 360. It has to be, because that is the square root of the eigenvalue for V1. So this right here is U1, all right? And similarly, AV2, when you work it out, is equal to, now of course this simplifies to, like it simplifies to 3 over root 10 and 1 over root 10, which is obviously a unit vector, right? And similarly, AV2 works out to the same thing, but with a minus on the second, like flip the components. After some simplification. So like, I'll get this straight eventually, guys. Well, let me just, butcher it here. U2 works out to minus 1 over root 10, 3 over root 10, all right? And so the SVD here is A equal to minus 1 over root 10, 3 over root 10. Those, I do a 3 and a minus 1 for the first column. U1 goes in the first one, and then minus 1 over root 10, 3 over root 10. The sigma part, which in this case is square root of 360, square root of 90, and then like that. I think, and then we have zeros over here, if I remember right. And then well, let me not, I won't write it out, but this down here, but transpose. So let me just tell you in words what's going on. So what the SVD does for you is it tells you that the transformation can be understood as basically three things. You take your input, you rotate it, and then you hit it on the sigma. Sigma does one of two things. It either projects a certain direction to 0, gone, or it takes other directions and just rescales them as appropriate by the singular values. Then the final thing is it takes that and it rotates it back. And that basically says any linear transformation can be written as a combination of a rotation followed by a projection / rescaling and then another rotation. This is a general prescription for how to understand any linear transformation. So anyway, that's all I can fit for today. So sorry, guys. If I had not miscalculated the V1, we might have had a better end game there. So sorry. As you guys know, end game's kind of horrible.